All right, let's dive in. Today, we're going to decode a fundamental chemical process that's happening literally all around you right now, even if you can't see it. It powers our world, from the tiniest battery to the biggest industrial furnace. We're talking about redox. So think about it for a second. What on earth could a rusty car, the battery powering your phone, and the very air you're breathing possibly have in common? Well, they all run on the exact same type of chemical reaction. And the answer, of course, is redox. By the end of this, you'll see exactly how they're all connected. So here's how we're going to break it all down. First, we'll cover the basics of what redox even is. Then we'll get into the great electron exchange that really drives it. After that, we'll learn how to keep score with numbers, meet the agents of change, and finally see this stuff in action out in the real world. All right, first things first, let's tackle that first question. What exactly is redox? We're going to start with the classic, kind of old school definitions that first got chemists on the right track. Way back when, it was all about oxygen. Super simple. Oxidation, that just meant a substance gained oxygen, like when iron rusts and becomes iron oxide. Reduction was just the opposite, losing oxygen. They later applied the same idea to hydrogen, just flipped around. It was a good start, for sure, but it doesn't tell the whole story. So let's get to the modern definition, because at its heart, redox isn't really about oxygen or hydrogen. It's about something way more fundamental, the electron. This is what we call the great electron exchange. This is what's really going on under the hood. And this is the key to the whole thing. If you remember just one thing, make it this. IRL. Just burn it into your brain. Oxidation is loss, reduction is gain. It's that simple. This little phrase is the key to understanding everything about redox, because it's always about the electron. So let's break that down. First step, the oil part. Oxidation is loss. Look here at this sodium atom, Na. It's neutral, but in this reaction, boom, it becomes a positive sodium ion, Na+, because it kicked out a negative electron. It lost an electron. That loss is oxidation. And of course, you can't have one without the other, so here's the rig part. Reduction is gain. A chlorine molecule snags 2 electrons and becomes 2 negative chloride ions. It gained electrons, so it got reduced. See? They're a pair. One gives, the other takes. It's a package deal. Okay, so electrons are zipping back and forth. But what about in really complicated reactions? I mean, how can you possibly keep track of it all? Well, that's where our chemical scorecard comes in. We call them oxidation states, or sometimes just oxidation numbers. This ladder diagram here is a perfect way to picture it. Just look at an element like manganese, Mn. It can have a whole bunch of different oxidation states depending on what it's bonded to. The rule is simple. The higher and more positive the number, the more oxidized it is. The lower and more negative, the more reduced it is. And actually using them is super straightforward. It's just a 3-step game. You find the atom's oxidation number before the reaction starts, then you find its new number after the reaction's over, and then you just ask yourself, did the number go up or down? That's it. So the rule is dead simple. If that oxidation number goes up, it's oxidation because it lost negative electrons. If the number goes down, it's reduction because it gained negative electrons. It's an absolutely foolproof way to track that electron exchange. Okay, so we know what's happening and we know how to keep score. Now let's meet the players that actually make the game happen. We're talking about the oxidizing and reducing agents. Okay, I know this next part can sound a little weird at first, so listen closely. The agent is named for what it does to the other guy, which means it's always the opposite of what happens to the agent itself. So an oxidizing agent causes oxidation in something else, and by doing that, it gets reduced. It's a total switcheroo. So let's boil it down. Oxidizing agents are the electron thieves. They cause oxidation by gaining electrons. Reducing agents are the electron donors. They cause reduction by losing electrons. And a pretty handy rule of thumb is that metals, which love to give away electrons, are usually good reducing agents. And nonmetals, they're often good oxidizing agents. All right, enough with the theory, right? Let's get to the fun part. Let's actually see what this chemistry looks like in the real world. This is where it all clicks. So to figure out how metals are going to behave, chemists use something called the reactivity series. And you guessed it, there's an awesome kind of silly mnemonic to help remember it. Please stop calling me a careless zebra. This list just lines up metals from the most reactive at the top down to the least reactive at the bottom. But what does more reactive actually mean when we're talking about redox? Well, it just means that metal is way more eager to give away its electrons. It's more easily oxidized, and that makes the more reactive metals fantastic reducing agents. They want to go out and cause reduction in other things. And check this out. This is a classic example in action. Zinc is higher on the reactivity series than copper. So if you drop a piece of zinc metal into a blue copper sulfate solution, the zinc willingly gives its electrons to the copper ions. The zinc gets oxidized and dissolves, and you see that blue color fade away. Meanwhile, the copper ions get reduced, turning into solid reddish-brown copper metal. That's redox happening right before your eyes. And speaking of visual clues, some redox reactions are just spectacular. They give you these incredible color changes. Take a look at these two common chemicals. When the powerful oxidizing agent potassium dichromate gets reduced, its solution flips from a bright orange to a deep green. And potassium manganate is even crazier, going from this intense purple to completely colorless. That color change is the proof that electrons are on the move. So there you have it. From a rusty fence and your phone's battery to these wild color changes in a lab, redox is this invisible engine running so much of our world. It all comes down to that simple transfer of electrons. The real question is, now that you know the secret, now that you can spot this invisible exchange, where are you going to see it happening next?